Good evening, technical directors, professors, and colleagues. Welcome to the 2022 ELECOMP Virtual Summit. We are Team Vicor, and our Capstone project is a probe interface hardware checker. Our technical directors that guided and mentored us throughout the semester were Alfred Binder, Product Engineering Manager, Nathan Shake, Associate Test Engineer and URI Class of 2020, and finally, Daniel Hartnett, Associate Test Engineer, URI Class of 2021. The designers that worked on the project included myself, Boston Lee, Electrical Engineering, and Giuliano Biondi, Computer Engineering. The company behind this project is Vicor, incorporated in 1981 with the main branch located in Andover, Massachusetts, and subsidiary branch located in Lincoln, Rhode Island, as well as overseas. Vicor has established itself as a dependable and recognized leader in the semiconductor world for power supply and power modulation. Some projects for power supply in the market include telecommunications, transportation, defense, computing, and many more. The project motivation for the company is that it will save time and resources due to any faults and errors being more easily found with the hardware checker. It ensures all the components off the probe board are actively working efficiently and effectively as intended. This would decrease the development time for similar cards and shift the focus on creating higher quality products as opposed to focusing on errors. The anticipated best outcome is for the team to create multiple hardware checkers that will be able to rigorously test each of their intended probe cards in order to confirm hardware functionality and completeness. On the left is a picture of resistor rings, and they are typically placed directly onto the probe card located on the right of the screen. This is to reduce or eliminate any current leakage. The key technical accomplishments for the semester included the execution of hardware checkers for the PO40 and PO52. Our best anticipated outcome was achieved with the completion of the PO52, the PO40, and the needle checker. During the semester, we were more efficient and effective due to gaining knowledge of reading schematics, writing code, and using the testers in the past semester. The economic impact the hardware checker has in the company is higher rate of production of chips with good functionality and higher quality. The hardware checker ensures the caliber of the chips and increases the productivity rate for more of them to be pushed out onto the market. With more chips in the market, more electronic devices can be made for the public, and Vicor's reputation and reliability would increase to companies and stockholders. This is a flowchart and describes the general usage of a hardware checker. First, you set up the probe card, then add the resistor ring, after you compile and run the code created for the specified hardware checker. Following running the code, the user will be given either no errors, which establishes everything is working correctly, or errors where debugging would commence. However, if there are no errors, the user would have to run the probe card without the resistor ring to make certain that it's a good card. If errors are presented with the removal of the resistor ring, then debugging would occur. This is a simple setup of testing hardware at Vicor at a wafer level. The cables come out of the tester as seen on the right, and then are connected to their specific locations on the probe card. The cables include timing cord A and timing B, which allows us to create tests on the timing page of the schematic. My technical accomplishments during the semester was creating a successful hardware checker in the PO40. From the creation of the checker, I was able to further add to my skills learned from last semester of reading schematics using Eagle test programs, which allows for on-demand debugging, as well as gain knowledge in the testing room with the ability to set up probe cards and attach any connectors needed. Here we see a schematic from the main page for the PO69. It includes matrices, APUs, drivers, and grounds. On this slide, we take a closer look at the site off the PL69 main page. In this case, site 1 in the portion of the code corresponding with the test, where voltage would be forced. We would first start the test by turning off the matrix C-bit K42 and force the voltage to expect 1000 microamps. In order to get the value, we would start by closing C-bit K26, then after, open the relay and matrix back up to ensure that the current reading is correct to get 0 microamps, since no voltage should be coming through. Here we see the schematic for the main page of the PO40. It includes matrices, APUs, drivers, and grounds. We test each pin similarly to the PO69, which is forcing voltage on the APU and closing any C bits needed, then after measuring current. To achieve the ABO, some of our key elements needed was communication with the technical directors, whether it be for professional or personal reasons. understanding the code and schematics, and how to apply them with the usage of the Eagle test systems for the creation and completion of many more hardware checkers in the near future. With all this in mind, I'd like to introduce my partner Giuliano Biondi, and he'll be leading us to the finish line for the remainder of this presentation.
Again, here's our flowchart that shows the process of how the hardware checker will work in a given scenario. In the beginning of the semester, my main priority revolved around receiving already completed hardware checkers, such as the PO12 bump, and walking through the test code and seeing what components or paths it tests. This allowed me to become familiar with physical schematics, which I have never done in class before. Then, I was asked to create a different version of the PO12. This allowed me to understand exactly how the hardware checker works and the reasoning behind it. After I grasped a good understanding of the hardware checker, I got the okay to move on to the PO52 probe checker, where my task involved creating the whole hardware checker from scratch. Lastly, my semester's capstone project finished off with creating a 100-pin needle checker. PO12 trim hardware checker was the first hardware checker assigned to me. I was given the bump version, which differs slightly from the trim version shown above. With the old outdated test code given in the bump program, I had to rewrite a new program for the PO12 trim, which differed in terms of paths, components, etc. On this slide is the main page of the PO52 schematic. Every path, pin, resistor, and capacitor will eventually be tested throughout the code. This is the first hardware checker I did not receive skeleton code for, and had to create the whole program myself. Every aspect of the schematic differed from the PO12. There was a new format for the timing and driver sections. On the picture shown above, there are net labels such as OC timer, which when creating tests for the timing page, we have to be aware of these labels to follow the paths to a different part of the schematic. One section of code that tests the pin on the front page of the PO52 is shown here on the right. The test involves using an APU or MAT as a reference point to send a volt and measure current across the designated pathway. GP_OC on the first line of the code lets us know what APU we will be using as a reference point, which you can see on the highlighted line is marked APU 5. Since the PO52 was created, debugged, and compiled and ran with no errors or alarms, I was given the OK to go on to the next project, the 100-pin needle checker. In the previous year, the Vicor project worked on a 70-pin needle checker that was created. Even though the project was a success, it is not a complete solution for every scenario. For it to reach its maximum potential, I had to expand on the project to make it able to test 100-pin needle cards. Above pictured is the Excel sheet I had to create. It was used throughout the project as a guide on what to create test code for. The red highlight is the current pin being tested, and the pins highlighted yellow are the surrounding pins. To ensure that the pins on the needles were working correctly and weren't damaged or destroyed, I had to create two types of tests. This involved a test to measure resistance across a specific pin and its surrounding pins, along with a capacitance test, which did the same. Figure 1 shown on the left is an example of the resistance test of pin 71 and its surrounding pins. Figure 2 on the right involves a capacitance test between pin 71 and its surrounding pin, pin 72. One of the pins is used to force current, while the other pin tracks the resulting ramped voltage. Once we have these, we are able to calculate the capacitance between the pins. The ABO of this project was achieved. The ABO goal that our team and technical directors set out for ourselves in the beginning of the year was to complete as many functional hardware checkers as we could, and to gather as much knowledge on all the topics that go into creating a hardware checker. Our team completed a total of 4 examples of these hardware checkers throughout the year. As a conclusion, I'd like to thank our technical directors and Dr. Sunak. Thank you for this opportunity and being there for us to excel our skills and putting our knowledge to the test. Thank you.